All right, welcome to Pre-Calculus 30, Chapter 9 review video. This is Chapter 9 on rational functions. All right, so let's do a little bit of review here. Talking about rational functions, okay? We've talked about all sorts of functions in Pre-Calculus 30 so far. We've talked about polynomial functions, which are just, sum or difference of regular, just terms, right? X to the power of whatever, 1, 2, 5. Just a sum, a polynomial of individual terms. We've talked about, what other kinds we talked about? We talked about exponential functions, where the functions exponential, the x is in the exponent position. Talked about log functions, so the logarithm of an actual number x. So we've talked about different functions, and usually the name gives us an indication of what kind of function it is. And so what's the root of this name? It's ratio, okay? So when we talk about a ratio, we're talking about something like 2/3 is a ratio, let's say. So if this is the type of function, what we're looking at is an x, but not up here, because that's a polynomial function really, right? Y equals 2x over 3 or 2/3 x. That's just a regular polynomial. What we're looking at specifically when we're talking about rational functions is where the x is in the denominator, okay? That's a big deal, because that has an x exponent of like -1 there, you see, and that's not polynomial. Okay, so here's some examples over here. Can be written in the form of a ratio of two polynomial functions, and specifically we want to make sure that q of x has a variable in it, like this. Okay, so we've got a variable in the denominator here, here, and as part of an expression here. That's what a rational function is. If we take a look at a graph of y equals 10 over x, this is what the graph looks like in blue. Now you should know this. Let me help you think about it maybe just a slightly different way. I don't know if I've mentioned this in my previous videos, but this is kind of a neat. I'm going to bring this up. You can also think of this, if you multiply both sides by x, you can think of this as x times y equals 10. That may help you in generating some points. So for example, if x is 2, then y has to be 5 to equal 10, right? So 2, 5. There we go. It's right there. If x is 1, well, then y has to be 10 to equal 10. So 1, and way up here, 10, you see? And it works with the negatives too. -1 is partnered with -10, and so on. So that might help. Your input variable is in the denominator here, if you look at it like this. Okay. The other thing you want to notice, really important, as x gets larger here, the y values start to get smaller and smaller on here, and they seem to, a lot of times, approach a certain value. And in this case, we're going to see that this would actually approach y equals 0 as it gets larger and larger, like that. And over here too, as x gets smaller and smaller, it's going to approach it's called a horizontal asymptote. We'll talk more about that later. All right, and then of course right here, x equals 0, that's the vertical line there, is undefined because you can't divide by 0, right? Okay. Okay, let's talk about those vertical asymptotes. Any restricted values in the denominator, okay, that do not get divided out when simplified, and we'll talk about that in a few moments, represent vertical asymptotes. So these are some of those examples again. So for this one right here, x cannot equal 0. So that means that x equals 0 is a vertical asymptote. Vertical asymptote. Over here, n can't equal 0, so it's the same thing. N equals 0 would represent a point that would be undefined, okay, or a section of the graph that's undefined. Over here, x cannot equal +5. How do we find that out? Well, just let that denominator equal 0 and solve. So if x equals 5, that's the point where we have a problem here. We're dividing by 0. That is the vertical asymptote at x equals 5. Okay? So that's just an introduction to rational functions. In 9.1, there's only 3 sections. So in 9.1, we're just exploring these rational functions and then talking about transformations. Well, good thing is we've been talking about transformations all year. So you know exactly what happens with transformations. If we take this graph, y equals 1 over x, which is probably the simplest rational function you could think of, it kind of looks like this. Remember, 1 times 1 is 1, or 0.5 times 2, right? So 0.5 up 2. 2 times 0.5, so over 2 up 0.5. So those are the collection of points that make this, the two sort of arms of this graph, right? Okay, so if I went ahead and just transformed this graph and moved it over to the right, let's see if I can do this, it would look like this. You see that? I've moved the black graph now over to the right. And if I moved the black graph up, it would look something like this. Ooh, this is pretty fancy, eh? So do you see how transformations work with rational functions as well? Now, how do we program that in? That's the question, right? What's a left, right? What's an up, down? Well, you've seen all this before. We have an a value, and we have an h and a k. Now, notice there's no b value, and that's a question that I get sometimes. We could include a b value here, but the neat thing about this is we don't have to. Now, why is this neat? Well, we don't really need a b value because this a right here is just simply a multiplier, and I can write it like this, a times 1 over x minus h. Okay? If you had a b, the b is not tucked away inside any kind of special function like a sine function or an exponential function, or, it's not really tucked away inside there. Really, b could be written like this as well, 1 over b times this. So what does that mean? Well, that means that a and b are almost like a combined constant on their own. Or a could be equal to 1 over b. So like I say, b is normally inside a function, and it's not treated the exact same way as a, but in this case, it is. So we just need 1a, okay? And I'll show you an example here just real quick from Desmos. So in this, I've got two functions lit up here. I've got where a, okay, so I've got a and b programmed into this function right here, just like traditionally we might see it. And if a is 2 and b is 3, okay, that would be 2 over 3. See that? So what happens if I just made one constant and made that constant 2 over 3? Well, I've got them both graphed here, and you can't really tell, but they're the exact same graph. Okay? So if a was 2 and b was 3, it would be the exact same as if I had another constant or another variable, and we can even call it a, be 2/3. It's the exact same. That's why we don't need a b, which is good for us. Okay? Now, in my opinion, this is probably the trickiest part of the entire chapter right here. This kind of question, all right? It's a very small percentage of what you're going to have to do. But if you have to transform an equation into this format right here, okay, it can get tricky. Most of the time, it's not a big deal. And I have this worked out for A and C. I also have a video. I have the attachment right here. And I'm going to put that in the description probably, and put a link here in the video if you want to watch this question done from scratch. But in A, it's really easy because what we can do is we can separate 11x over x and add 12 over x. And what we really want is to get rid of the x in the denominator, in the numerator, right? And show the x just in the denominator. So this one's pretty easy, right? This one, not so easy. Not so easy at all. But the key here is to add and subtract 1 from the original equation. Now, what do I mean by 1? Well, 1 is going to be represented by whatever this is over itself, x plus 6 over x plus 6. And you can add any multiples of this. You can add 2 of these, or you can add 12 of them, or whatever, as long as you subtract 2 or 12 of them over here. So by adding and subtracting the same thing, we're not changing the equation. Okay, that's the most important thing. And the second most important thing is that when we do this, and I group these two terms, look what happens. I have the negative x plus a positive x. That gets rid of the x in the numerators here. And so this right here simplifies to this part. And what is x plus 6 over x plus 6? That's just 1. So here we have now this equation written in the form of this right here, where there's no x's in the numerator. It's written as a rational function. Okay? So that's the trickiest part. Again, watch the full video if you want some more explanation there. But let's move on to 9.2. Okay. So 9.2, we're analyzing rational functions. On the surface, these two functions in red here look very, very similar. Okay? And you'd think, oh, the graphs probably look really very close to being the same, but they don't. The big thing is we've got a x plus 2 in the denominator here and an x minus 2. First thing you should always do when you take a look at these things is you should always factor, okay? Always. So factor the numerator and the denominator, and something just disappeared on me. Factor the numerator and the denominator and see what you have to work with. And when I say see what you have, over here on the right, what you want to notice when you factor is that we actually have common factors on the top and the bottom. And so those really can be simplified. You want to make sure you note the factor that you're getting rid of, okay, on the bottom especially. So you know that we have a restricted value here, x cannot equal -2. And I have that written down here, but before you eliminate this, okay, oh sorry, you can't maybe see that. Before you eliminate this, you should note your restrictions, okay? That's in one of my other videos as well. Make sure you remember that. But when this is all said and done, look what happens here. This one on the right simplifies to y equals x minus 1. That's the simplest version. And over here, clearly it's a rational function. So if we graph each of these, even though they look the same, they're actually going to manifest themselves very, very differently. Okay, so the blue graph is still a rational function with a vertical asymptote at x equals +2, and that's what we see here, you see. Okay, it's got those traditional kind of lobes there. But the red graph, okay, really it looks like y equals x minus 1. That's what it simplifies to, with the one exception that x cannot equal -2. And at x equals -2, which is highlighted right here, actually the graph does not have a y value. Whoops. Oh goodness, let me just undo that. Whoa. So here I zoomed in at the bottom. See this? I zoomed in on Desmos, and I zoomed in right at this spot right here. Okay, that's the zoom here. And what you see is that it's undefined at that point. Just that one point is no good. Okay, and this represents something called a point of discontinuity I have over here on the right. Oh, I can't move that over now. Anyways, so a point of discontinuity is a point where the graph ceases to be continuous. Okay, there's a missing spot. It's kind of like a hole in the graph. Okay, it's a single point that's missing from the graph because of the restricted nature of that x value. And so when you divide out a common factor from a rational expression, then you're going to end up with a gap. Okay, it's called a gap discontinuity. Okay, so there's a vertical asymptote when the factor stays in after simplification. That factor remains there after everything is divided out and simplified. Vertical asymptote. If the factor is gone after simplifying, it's a gap, a hole, a gap discontinuity. All right, with me? Okay, we're going to talk about horizontal asymptotes real quick here. Horizontal, so that's sideways, okay? If the degree, now look at the polynomial on the top here and the polynomial on the bottom. If the degree of the numerator is less than the degree of the denominator, like this situation, the horizontal asymptote is always y equals 0. So this may or may not make a lot of sense to you, but just think about this. If you want to always look at the leading coefficients of your polynomials, 3x and x squared. My reference, what I think about when I simplify just these two, is 3 over x. Okay, what does that do? Well, if x gets really large, and really we're talking about an asymptote that the graph would approach as x gets really large or gets really small in the negative direction there, but I think about getting large always. And when x gets really large, like let's say like a billion here, what's 3 out of a billion? That's pretty small. So that's pretty much 0. So, you know, when you have an x in the denominator and just a number on top, as x gets really large, this value gets really small. So you're approaching 0. That's your horizontal asymptote. And that works for every rational function that has a degree on the top less than the degree on the bottom. And you can check it out if you want. So what happens if the degrees are the same? Okay, well, again, I look at the leading coefficients of each of the polynomials on the top and the bottom, and I simplify that. Y equals 3. Well, guess what? As x gets super large, y becomes, well, 3, because it doesn't affect this. So you can see on this graph, 1, 2, 3, here's 3, and that is our horizontal asymptote. Okay, so when they're the same, you simply take, it says here, you take the, where is it? The ratio of the leading coefficients of the numerator and the denominator, and that is your horizontal asymptote. Okay, so this is 3 over 1. That's the horizontal asymptote. And over here, this is a special situation where the degree in the numerator is greater. Then you have an asymptote that is not horizontal. Okay, you either have no discernible asymptote at all, or it's kind of on an angle or something like that. It depends. So this is the graph here, and you're going to have some kind of asymptote really that's kind of crazy, like kind of like this, right? So it's curved and whatever. So again, if you take a look at the leading terms and you simplify that a bit, if you see a cubed here or a squared or anything like that, think about x getting really large. If x gets really large, this y is even larger. Like there's no value that it kind of centers in on or approaches, right? It just approaches infinity. So there's no horizontal asymptote. That's all you need to know. Okay, we'll study more about this in calculus next year. All right. So again, I just want to do a little blitz here of this example. If you're given equations to match with graphs, there's a few characteristics you want to take a peek at. So again, I'm going to have this on the screen. Let me just zoom out a bit so you can see all of it. And again, so what are we going to do here? So A, again, factor, right? Factor top and bottom so you can see what's going on. And I factored and I realized that, hey, I have a gap discontinuity at x equals -2. Let's see. Oh, wow, that's handy right there. Okay. And I also have a vertical asymptote at x equals +2 because this factor did not get simplified out. So x equals +2, there should be a vertical. And right away you're seeing that a of x is graph 2. Okay, so just take a peek at some of the characteristics. Let's do this. Let's do C next. C is a little bit easier than B. So if you factor C of x, then you know what? You have two factors in the bottom. Neither of them get divided out. So that means we have two vertical asymptotes here at -2 and +2. Those are easy to spot on graph number 1. All right, so B of x, this is maybe a bit trickier. I'm not really sure. One thing you can notice is that the degree on top is less. So we're going to have a horizontal asymptote at y equals 0. So that is when x gets really large or really small. It's going to approach y equals 0 there. But being that this is graph 3, and we know that by elimination here, I wanted to highlight this. This does not look like it approaches 0 necessarily, but as it gets larger, it will come down and approach 0. And this one kind of crosses over 0. And you know what? If this goes smaller and smaller, it actually kind of creeps back up and approaches 0. So in this area of the graph, the asymptotes don't mean anything. Okay, so it can cross y equals 0 even though that's the asymptote. It can cross that in the middle of the graph. It's only when x gets really large or really small. Okay. All right. Yeah, I mean if x is 0, you could just try an intercept. If x was 0, what would you have? You'd have 0. If x was 0, 0 over 0 minus. Whoa, wait, what? Oh, sorry. That's the wrong one. I'm looking at this one. If x was 0, we'd have 4 over 1. Sorry. There we go. See? If x was 0, I'm trying to find the y-intercept. X is 0. That's gone. 0 and 0. So it's 4 over 1. 4. All right? So just take a look at the characteristics of graphs. Try and match characteristics of graph. Okay, final section here. 9.3. And this one really is solving again. So we've talked about transformations and solving all these different kind of functions, right? So we are solving algebraically and graphically. So solving algebraically, we want to try and isolate x if we can. A lot of times we can't. A lot of times these complicated things kind of boil down to maybe a quadratic or something. But the bottom line is you want to factor again. Okay, factor is a big thing. Factor top and bottom, see what you have. And here's a solution here. So we factored. And on the right side, notice we have 2x plus 5 as a factor in two of these pieces. And then we have 2 also as a factor in one of the denominators. So we're going to multiply to get rid of the denominators. Okay? And we're going to multiply by the factors that are in there. So we're going to multiply by 2x plus 5 and by 2. And when we do that, let me zoom back in here. When we do that, we'll see that we will be able to get rid of all the denominators. It's going to be a bit complicated, so you have to wade through it a bit, but you'll see that you'll get rid of some of the denominators. So in this case, the 2x plus 5 and the 2x plus 5 here, okay, that's gone, so it's just going to be a 2x, there you go. And when you multiply this thing times this one, the 2, this is going to be, 2 times 2x plus 5 times 2x. You got to multiply all those and you get that right there, I guess. And then, yeah, when you do this side as well, again, these two go with that, and so you're just left with the 8x plus 15. Okay, so multiply by the common multiple there, I guess. Yeah. All right, when you get to a point where you have a quadratic, you can solve by, however we did that before, using quadratic formula if you want, or factoring by intuition and using the zero product principle, which is what they did here. And you're going to have to check your values though, right? You're going to have to check. Notice that one of the values that the algebra gives us is -5/2. Well, we should notice our non-permissible values early on in the question, which they did here. And so that means this one is not going to be acceptable as a possible answer. And so you realize that that makes the denominator 0 over here and here. So you would reject -5/2, and your answer is 3/4. Okay? So algebraically, get rid of denominators, gather all like terms, solve however you can after that. And then, of course, if you want to do it by graphing, you can take the left side of the equation, graph the corresponding graph for that, so y equals this, and then on the other side, y equals this one on the right, like they did here. Graph them both, you see the graph on the right. There is one intersection point right here, only one, and the x value is 0.75. There's your answer. It looks like they might intersect up here somewhere, but guess what? This is actually an asymptote, and they're both approaching the same asymptote. So they look like they're touching, but they actually aren't. Okay? And if that's too confusing for you, then the final thing I'm going to show you is, of course, one of the ways that you can solve by graphing is by moving everything over to one side of the equation and then graph that one equation. So notice this is the original question. I moved this big thing over to the other side, and I made it y equals. Okay, so I graphed this one equation, and this actually simplifies to a straight line here. Cool. And the x-intercept, right? The x-intercept here, the x-intercept will be the solution. So when you graph just one equation with everything combined, the x-intercept or intercepts will be the solution, and so there you go, 0.75. All right, so that's chapter 9, talking about rational functions. Hope that little review helped. A variety of questions. Please see other videos if you want more instruction on some of these things. So I hope your exam goes well, and there you go. Have a great day.